Hello everyone, my name's Jared Beckwith and I'm here today with my genius brother and engineer, Christopher Beckwith, and we're here to give a presentation on how we attempted to detect abnormalities in EEGs using persistent entropy. Here's the basic overview of an EEG for those of you who are unfamiliar. So an EEG records the electrical activity of the brain, and as an EEG technologist, I place metal electrodes onto the patient's scalp in order to record this activity. Now this test is best used to help the doctor diagnose and treat seizures. So a lot of work goes into labeling all these seizures. It takes highly trained medical professionals to recognize these seizures and label them. So the technologist, best case scenario, they'll be able to record and label all the seizures. And the neurologist, that'll make their job really easy so they can see it and confirm and make the final decision so they can make the best diagnosis and treatment plan possible for the patient. Here's a screenshot of an EEG if you've never seen EEG waves before. It's just a bunch of squiggly lines, to be honest, but it takes highly trained professionals to learn how to read these things. So I was just teaching my brother Christopher about montages. That's one thing that I would like in the future, to him be more experienced with the different montages, the bipolar montages versus the reference montages. And once he's more familiar with that, I think we'll be able to get better results in the future. The study that we looked at was done by Piecewise, and in 2018, he found that persistence entropy differs significantly between EEGs containing seizures and those not containing seizures. So if you look at the graph here, it shows the persistent entropy on the y-axis. You can see a clear separation of the blue being the normal patients and the red being the abnormal patients. So if the persistence entropy came out to be above 0.827, it was found that the patient was normal. If the persistence entropy was below 0.827, it was found that the patient was abnormal. Well, at least that's what happened in his study of pediatric patients. So the engineering work that my brother Christopher did looked at the Temple University Hospital EEG corpus, and it closely tried to replicate Piangerelli's study, although Piangerelli did his with pediatric EEGs. So Christopher calculated the persistent entropy of EEGs to test whether it could potentially be used to differentiate between 20-second segments of focal seizures versus 20 seconds of just normal background activity. Another experiment he did was to test between 18-minute segments of EEGs labeled as normal versus 18 minutes of EEGs labeled as abnormal. Before analyzing the data, we have to do a step called preprocessing. If you're an EEG technologist like myself, I'm sure you're familiar with all different types of artifact and know all about the filters on your EEG equipment. So a filter that we use all the time is called the notch filter, or the 60 Hertz filter, to filter out electrical interference from all different stuff that could be plugged in the ICU, or even just the bed being plugged in itself can help create 60 Hertz artifact, which distorts the EEG signal, and it's hard for the doctor to see what's going on. As you can see in the top right, there's a good 60 Hertz artifact, and on the bottom, that's where the artifact is filtered out with preprocessing by using the notch filter. So we have to filter our data before we can analyze it correctly. And then piecewise filtration. So this is where it starts to get a little complicated. So what is the piecewise filtration?
So there's our EEG signal.
Okay.
But we're only really looking at certain points from the signal, which are the black dots. So we've connected those black dots with lines between them.
Okay.
And we start at the bottom. You see, each time the line moves up, see it starts on that one. Each time the line moves up, that's one simplicial complex in our sequence of simplicial complexes. So first one is just that point. Next one, those 2 points. Next one, those 2 points, and then that point and the line between them, until eventually you have the full thingamajig.
Okay. Yeah, that would be interesting on the 18-minute ones, because that's a much longer signal. I'm sure a lot of computing goes into that for the piecewise filtration.
But luckily in R, it's just one function.
So pretty easy when you're coding in R.
Yeah.
So this is what creates the barcode.
It's a little more complicated than that. So you have a filtration and you have a sequence of simplicial complexes, and then the barcode tells you how the connectivity changes as you as you go through those simplicial complexes in order. So like the y-axis, that's our filtration parameter.
Okay.
And then the barcode tells you the x-axis of the barcode is the filtration parameter. So it tells you how long the zero-dimensional holes last.
Wow.
Zero-dimensional hole is just like, is it connected or is it not connected? If
it's
connected,
okay.
that's a zero-dimensional hole. Or yeah, I guess connected components is a better way to phrase it.
Okay. So and this brings us to the persistent entropy.
Yep, and then once you have the barcode, you can calculate the persistent entropy using that formula.
Okay, so there's the barcode, and then using that formula, we calculate persistent entropy, which is the same number that the Piangerelli used in his study to determine whether it was seizure or normal EEG.
Yep.
Which above 0.82 was normal, and under 0.82 was abnormal. Okay. And you just do that with that formula right there, and then you normalize it between 0 and 1, so that way you can, see if it's 0.82 or closer to 0.
Yeah.
Okay, that makes sense.
And we do that for each signal in the EEG and take the average to get the final number.
Oh, okay. Okay. So with like all the channels?
Yeah. So the average of all the channels is what he used.
Interesting. So would that be different to detect like focal seizures in one specific spot compared to a generalized seizure where it's every single channel pretty much?
Yeah, possibly. Maybe if you're just looking for focal seizures, you'd only want to consider specific channels, but then like you don't know which.
Yeah, you don't know where the focal seizure is coming from. But I guess actually if someone has had EEGs in the past and they've already had marked focal seizures, then you'd know pretty much which area to look in.
Yeah, but if Piangerelli's technique is as good as it's supposed to be, then we shouldn't need to worry about looking at specific areas.
Yeah, exactly. Okay. So we'll just keep investigating on Piangerelli's technique. Okay, and we got the results, pretty much unremarkable, not really a correlation, and you think that's due to what reasons?
Maybe that 20 seconds is just too short.
Yeah.
Too much random stuff going on.
Yeah, you might need like a longer data size, I guess. I guess that's why it's recommended to have the EEG at least 20 minutes. That's like the national recommendations or whatever. At least 20 minutes of uninterrupted EEG. So you usually do about 30 minutes because you also want to do photic stimulation or hyperventilation if the patient can take it. Okay. So you might want to actually try looking at 30-minute or 25-minute or something, or 20 minutes.
Or hour, like Piangerelli.
Or an hour, exactly. Okay. And then no downsampling, you think those are more accurate than the other ones because it's already small. Like there's no reason to downsample it in the first place.
Yeah, there we got the full 20 seconds we're looking at. So.
Okay. And then the final one is the normal versus abnormal, where the abnormal might not necessarily be a seizure EEG. It could just have like delta slowing and not exactly have a seizure.
Yeah.
Okay. We're going to try and replicate Piangerelli's studies more closely with adult EEGs because he did it with pediatric EEGs, right? So we're going to try it with adult EEGs next. And then we'll see if we can replicate his results and see if there's like a threshold number of if it's above this, then it's normal, and if it's below this, then it's abnormal. All right, it's a good plan. Thank you so much for watching. If you want to sign up to be one of the first 100 beta testers of my automatic EEG annotation software, go to AiONEEG.com, or if you're an engineer interested in this subject, feel free to reach out to me on LinkedIn or the YouTube comments. I'm going to be hiring for this position to help automatically annotate EEGs. I need as much engineering help as I can get. Again, thank you all for watching and have a nice day.